Okay, this video is to help students with notes for the introduction to calculus and limits. We've already had notes on limits, determining limits numerically, determining limits graphically, and determining limits analytically. So what I want to do with this one is find limits and talking about the continuity with limits. So the first example I have here is the limit as x approaches 2 of 1 over x. To find this numerically, I'm going to use a table of values. So I would have x is my independent variable. F of x is equal to 1 over x is my dependent. So I want to pick values that get close to 2. So I'm going to choose on a number line numbers left of 2, like 1.5, 1.6. But I'm going to get closer and closer to 2. So I'm going to choose 1.9, 1.99, 1.999. I can even put a 2 in there if I want to. But then I want to get to the numbers to the left of 2. So I would have like 2.5, 2.1, 2.01. So the numbers that are getting close I'm going to choose are 2.001, 2.01, and 2.1. And I would use the calculator and fill in the numbers. So I'd have 0.526, 0.502, 0.500. At 2, I'd actually get 1/2, which is 0.5. 0.4997, 0.497, and 0.476. And remember, I'm just using my calculator and the table of values to find these numbers. So as you can see, the limit as x approaches 2 of 1 over x would be 0.5 or 1/2. If I look at something graphically, I would actually sketch a graph of it. So if I type it in my calculator, this is a rational function that has 2 portions. And when x equals 2, here's 2 right here. And if I come up here, my y value is 1/2. So once again, that's verifying what I found numerically. Graphically, the limit as x approaches 2. And when I'm saying when x approaches 2, I'm coming from the left and I'm coming from the right, getting close to 2. And analytically, I'm just going to plug in. So the limit as x approaches 2 of 1 over x, put a 2 in for x, I get 1/2. So they all give me the same answers. And sometimes it's better to use one over the other, but this was just an example to show you all 3. Now we're going to start talking about continuity. A function is continuous at c if the limit as x approaches c of f of x equals f of c. So for an example, this function f of x equals the square root of 3x minus 4. Well, I know what the graph of that looks like, but I want to see if it's continuous at x equals 2. So what I'm going to do is I'm going to do the limit as x approaches 2, because that's what I want to see if it's continuous at that, of the square root of 3x minus 4. I can do this numerically, I could do this graphically, or I can do this analytically. I'm just going to do this analytically. So I'm going to have the square root of 3 multiplied 2 minus 4. Square root of 6 minus 4 is the square root of 2. Then I want to check f of 2. F of 2 is going to equal the square root of 3 multiplied by 2 minus 4. Square root of 6 minus 4 is the square root of 2. Since the limit as x approaches 2 of x approaches 2 of the square root of 3x minus 4 equals f of 2, the limit, or the function is continuous at x equals 2. And so in calculus, that's the big part of it. It's not just that you answer your question as yes or no, but that you can verify your answer. And this definition told me it's continuous at the number c if the limit is equal to the function value. So that is enough to show that I understand. Now we're going to just discuss removable discontinuities. A removable discontinuity exists when a whole can be removed by redefining the function as a single number. And you first started talking about these in Algebra 2. So we're going to look at this and determine the removable discontinuity for this function. And then we're going to find the value that actually removes the discontinuity. So this is x cubed minus 27 over x minus 3. I know it is discontinuous at x equals 3. So I'm going to factor the numerator. So I have x minus 3, x squared plus 3x plus 9. And my denominator stays x minus 3. Here, my numerator and my denominator have the same term of x minus 3. So I don't need that. So that shows me that my discontinuity is at x equals 3. Okay, I'm saying, let's make this a little bit nicer, 3. I'm saying this is removable because when I factor out the numerator and the denominator, I can then plug in 3 for x. So 3 squared plus 3 times 3 plus 9. 9 plus 9 is 18. 18 plus 9 is 27. I could not put a 3 into this original equation because I would have gotten 0 over 0. Once I factored this and got rid of this x minus 3, I now can put a 3 in for the x. And when I put a 3 in for the x, I get 27. So I'm going to have the point 3, 27. It's going to be where this is removable. That's the removable discontinuity. So the limit as x approaches 3 of x cubed minus 27 over x minus 3 is equal to 27. So 27 is the value that removes that discontinuity. If you were to graph this, I'll leave that for another day. Well, let me show it to you. If I graph this, I'm going to grab my calculator. And I want x cubed minus 27. Remember, I don't want the function that's already been simplified. This is the function I'm actually looking at. So there's my function. And I don't see the whole thing. I'm in a standard window. I want to see what's happening at the point 327. So I'm going to change my window. And you can hit zoom out if you want. I prefer my students to understand changing the window. I know I want to go to when the y value is 27. So let's go up to y max of 30. So here's my function right there. And when x equals 3, I'm getting closer and closer. You can see my x values. I'm at 2.1, 2.3, 2.5. That's really close to 3. And it's not going to go right on 3. So what I'm going to do is change my window. So I'm looking really close at 3. So let's go from x min of 2, x max of 4. And my y min, let's make this 28. And my y max 30. No, I want to go to 27. So I want to make y min of, say, 25. And my y max 29. Sometimes you can actually see the hole, and in this case you can. Right there where there's a space, that would be a hole. On a paper, if you were to draw that, you would put a circle around that right there. So that is called a removable discontinuity. I can remove that discontinuity by plugging in the point 327. On a piecewise function, what it would look like is I would have f of x equal to x cubed minus 27 over x minus 3 when x is not equal to 3. Then I would want it to equal 27 when x equals 3. So you're basically taking this discontinuity that's created here and plugging it up with this value. Non-removable discontinuities, I cannot fix it. It's like I can't, there's something wrong and I cannot fix it. So it occurs when there's a jump or an infinite discontinuity. And we've talked about these before when limits fail to exist. So the type of discontinuity for each function, and we want to know where this discontinuity works. For y, f of x equals tangent x. Remember the tangent x? The graph of that tangent looks like this. And what happens is it's got all these vertical asymptotes. So this would be at the origin 0, 0. This vertical asymptote occurs when cosine is equal to 0. Cosine is equal to 0, negative pi over 2, pi over 2, 3 pi over 2, and so on. So in this case, I'm going to say x equals pi over 2 and x equals 3 pi over 2 are vertical asymptotes. I cannot fix that. I cannot replace that value with anything to make it continuous. So in our textbook, it would be x equals n pi plus pi over 2. All the multiples of pi over 2 have a discontinuity of a vertical asymptote. If f of x equals greatest integer of x, some books put it like this, some books use different forms for representing it. It would graph like this. Any greatest integer function looks like this. So there's a jump. When you go from one value to another, there's a jump. So there's going to be jumps at all integers. And these are not the only examples for non-removable discontinuities. Anywhere that there's a vertical asymptote or anywhere that there's a jump, there's going to be a non-removable discontinuity. And then the last thing we'll talk about is the concept of one-sided limits. And every time I teach this, I still talk about one-sided limits. You just don't realize I'm talking about it. What's happening with this graph, let me zoom in a little bit closer. This graph is continuous, and then it stops here, and it's not including the point, but that's irrelevant. It doesn't matter if it's including it or not including it. But then it jumps up to this part, and it's doing something different from then on out. So we're going to talk about right-sided limits, and I'm going to zoom in as close as I can get so you can see this better. You have to be very careful. A right-sided limit is red. The limit is x approaches c, that will be some number, from the right. That little plus sign as a superscript means it's from the right of a function. A left-sided limit would be red. The limit is x approaches c. From the left side, there's a little minus sign as a superscript of the function. So I'm going to look now at piecewise functions to start with. So piecewise functions, I've got f of x equals 2x if x is less than 0. If I were to graph that, anything less than 0, so it's left of 0. So if I had a negative 1, it's negative 1, I'd have negative 2. It's a point. If I had negative 2, I'd have negative 4. And this function keeps coming up here. till it gets to the origin. This 2x plus 1, I have a y-intercept of 1 and a slope of 2. And I want everything to the right of 0, and I'm going to include 0. So at 1, I have a closed circle, and I have a slope of 2. So here's the graph. What I'm looking for, the first one, is the limit as x approaches 0 from the left of f of x. So if I look at this graph, from the left is coming here. And I want to know what's happening as it gets close to 0. As it gets close to 0, the y value it's approaching is 0. So the limit would be 0. I'm not asking what is the value at 0. I'm asking what happens as you get close to 0 from the left. This function limit is asking me for the limit as x approaches 0 from the right. So from the right, I'm coming this direction to 0. So my limit is this y value, which is 1. So the limit from the left of this function is 0. The limit from the right of this function is 1. Is this function continuous? Definitely not. The limit from the left and the limit from the right are different. So this is not continuous. Here's another one. If I draw a quick sketch of this, I know the absolute value of x looks like this, but I only want the portion less than or equal to -1. So if I put a -1 in for x, I'm going to +1 for y. If I put a -2 in for x, I get a +2 for y. And this is saying x squared. X squared looks like this, but I only want the part greater than -1. If I start at -1, -1 squared is 1. It actually starts there. This would be an open circle, but since it's already on top of a closed circle, that's good. And then I have 0, 0, 1, 1, 2, 4. That's what that function looks like. Now if I look at the limit as x approaches -1 from the left, so -1 from the left, I'm looking at it this direction, is equal to 1. The limit as x approaches -1 from the right, so here I am coming from the right, I'm coming this direction towards -1, is also 1. So this function is continuous because the limit as x approaches 1 from the left is 1, and the limit as x approaches 1 from the right is 1. And you can see this. It's continuous, there are no breaks. The last example I have, I'm looking at this, and this is a little bit different function. I'm going to graph it on my calculator to show you. So I've got x squared minus 5x plus 4 in my numerator, and x minus 4 in my denominator. My window's still from 4, so I'm going to hit standard window, zoom 6. Okay, that looks like a straight line, but I don't know if it's continuous. If I look at where x equals 3, so if I go to my table, let's go back to automatic, asking for x, and I look at when x equals, actually let's look at x equals 4. I get an error. It doesn't look like it's continuous there. So what's happening is it looks like a straight line, but if I look really close when x equals 4, so I'm going to change my window. I'm going to do from 3 to 5. You can barely see. There's a hole right there at x equals 4. And what's happening is it's this function whenever x is not equal to 4, and its value is 3 when x equals 4. There's my removable discontinuity. So what's happening And as it looked like this was x equals 4. That's this upper function. Then this lower function will say when x equals 4, I want y to equal 3. So I'm going to fill that in. That's an example of a removable discontinuity. If I factor this function, so I get x minus 4, x minus 1 all over x minus 4. My x minus 4 over x minus 4 is 1. So I have x minus 1 in the numerator. If I replace x minus 1 with 4, so 4 minus 1 equals 3. This is my value for my removable discontinuity. So what happens as x approaches 4 from the left, I'm getting closer to 4, this value is 3. As I'm approaching 4 from the right, this value is 3. So if I only had this top function right here, that is not continuous when x equals 4. By adding this part of the function, I'm making a continuous function. I've plugged the hole, I've made a removable discontinuity.